Yeah. Rita is our guest for this week in here, and she got her PhD in 2011, originally from the Carnegie Mellon University and the New University in Lisbon. And then after some postdoc and visiting research position, she is a scientific research scientist at the Kingston University in Saudi Arabia. And she's an expert in homogenization, calculus of variations, and material science, I would say material science. And today she will speak about nonlocal denoising model and biological parameter.
Thank you, Martin, for the introduction. Thank you for the kind invitation and the reception I've been having so far. Just one day, and I'm already thrilled and looking forward for the remaining of the week. I'm really happy to be here and also for the opportunity to give this talk. So let me first mention my collaborators, and these are Elisa Davoli from the Technical University in Vienna, and also Caroline Feisbeck and Ed Schonberger from the KU University in Germany. And the work that I'm going to describe here, this joint work, our motivation in the background are, say, noisy image, damaged image. So you are given a noisy image, say with blur, with noise, and you want to restore it. And so this is at the background motivation of this problem. And one successful approach to address this problem of restoring images, called the restoration problems, is through a variational approach. And roughly speaking, in general, it goes like this. So this restored image, the reconstructed image, is achieved as the minimizer of a certain functional. And typically, the functionals that you get in the literature, they are an equilibrium between two terms. One, the fidelity term, that essentially it measures the distance to your noisy image, and saying, I mean, putting this metaphoric way, if you start with a cat, you don't want to end up with a dog. So there is some fidelity to it. And here it is measured in terms of the outer norm. And then you have this called the reconstruction, sorry, the filter or the regularization term, which regularizes your image. So for example, removes noise. Okay, so there is a competition between these two terms. You want to find the minimizer for this functional, and yes, as usual. So omega is the image domain. This U8 is going always to stand for the noisy image, and as I said, this R is the regularizer. And a very important example. It was a milestone in this business of image restoration in this variational approach. Is when you take as a regularizer the TV, or a multiplier of the TV, the total variation, because this simultaneously allows for noise removal while preserving edges. And edges is something that you get naturally in an image. And there is this parameter alpha that actually is going to be a central player in this talk, but let for the moment just say that this is a parameter that from the analytical point of view, for alpha, a positive number, it does not change the analytical study in regards to existence and uniqueness. Doesn't matter, it's a constant, but as you'll see, it will be a central player in this talk, and you'll see it in one slide. But before going to that, let me make an observation about this variational approach. It is extremely versatile in the sense that you can pick whatever you want for fidelity, you pick whatever you want for a regularizer, and you get a model. Of course, at the end of the day, you get what you pay for. So you better choose, this means you better choose a good regularizer, a good fidelity term, but you pretty much you are free to choose both the regularizer and the fidelity term. And it turns out that an important, or at least that a type of regularizer that has been receiving lots of attentions are these non-local, are regularizers that incorporate non-local effects, for example, those induced by different quotients or involving fractional operators. And the reason people have been paying lots of attention to this kind of non-local functional is because, well, on one hand, it does not require so much regularity. So you can work with functions that are less regular than the local counterparts. And also they have been shown to lead to more efficient numerical algorithms. And the reason I'm pointing out these non-local operators is because though our theoretical framework is not restricted to non-local operators, as you see, it will apply to both local and non-local. Now, in the back of our mind is these non-local operators, and when I get to the applications, you will only see non-local operators, okay? But actually, the theoretical framework is not restricted to those. Now, let me go back to this parameter that was appearing here, and like I said, from the point of view, if you want to study existence and uniqueness of solutions to this problem when you replace R by constant times the total variation, it does not change anything. But from the numerical point of view, it actually plays a central role. And actually people used these parameters as a tuning as a tuning for accuracy. So changing this parameter will change the accuracy of your reconstructed image. Let's see, let's have a good feeling in this TV model. So what is the role of alpha here? So if you take alpha very big, we are in a minimization problem, so we want the lowest energy possible. So if alpha is very big, this means in the minimization process, you want TV very low, right? You want to compensate. And so if it is the TV is too low, then it's too regular. You are over smoothing. So a very big alpha makes TV very low. You cannot oscillate that much. You regularize too much. On the other hand, if alpha is too small, TV can be very wide. So pretty much you don't restore. You are not regularizing at all. And actually can prove that the minimizers, these U alpha, which are the minimizers of this TV model, they converge to the noisy image as alpha goes to 0. Okay. And so then the question is, then how do you choose the best possible alpha? And initially this was done manually, image by image, which of course, as you can imagine, this is impractical. And in particular, given the amounts of images that are generated every day, this is not practical. And this gave rise to this optimization bi-level skills in the flavor of machine learning, and to try to find the optimal alpha for a given class of images. And the story goes more or less like this. And by the way, the were introduced by the Los Sean Lieben Volkomer group in Cambridge in imaging studies. And so say that you are given a training data. So this is your perfect data. You know the noisy image, but you also know the clean one. This is a training data. You know this. You know these guys. And then how do you do it? Well, there is this, let me start actually with the lower level. Now it is written in the correct way. And the lower level, it is just what you have seen before. Fix an alpha, then you just find the minimizer of your TV model. This is as before, this is for alpha, you get your corresponding reconstructed image. And then there is this upper level, that's when you find your optimal alpha. And the optimal alpha is the one that minimizes an error. So what is the error? Here it is measured in terms of the auto norm between your clean image, it is your data, you know this, and the reconstructed, the function that your model is giving back to you. And this difference is the error that you are making, measured in terms of the auto norm, and you want to minimize this. And then it gives you the optimal alpha. And then how is this used in practice? Well, the idea is that if you are given a class of images that are in some they are in some sense similar, then the idea is to use the same optimal alpha for those images. And if you want like analogy, I like this analogy. For example, if you go to a music show, an opera, I don't know, and use a binocular, right? And you want to see in detail, depending on my imperatives, I will adjust my binocular in a certain way, right? This is, I'm adjusting my alpha, and then I find my optimal. But if I give to someone else, it will have a different optimal alpha. But then how can I use this in an optimized way for me? Well, if it is always me, I use the same binocular. If I am, say, within the similar show at the same distance, I don't have to adjust each time. I found what is best for me. Okay, so this is, I'm going to use this optimal alpha for similar images. Okay, so this is somehow the idea behind how we can use these semi-supervised learning schemes in practice. Okay, and then from the mathematical point of view, of course, what you want to prove that such bi-level schemes, they have solutions, and what are optimality conditions for proving solutions. And well, these problems have been in the literature, I've been studying in the literature quite a bit. Here, there is a list in the next slide. There will be some more. It's not exhausted by any means. There are some contributions for the Cambridge group, from the Berlin group and Kras group, for instance, and these were dealing with real valid and special dependent weights. There are two more in this flavor, and let me also mention, and one of the duplications that I hope to have time to present deals with this spectral fractional Laplacian, where they were trying, these works were trying to find the optimal fractional parameter. Now, what is common in all these works that I'm mentioning here and some more is that there is some kind of a priori compactness that it is imposed on the admissible parameters, which may lead to in some sense, suboptimal results. Let me give you an example. What people usually do, what is common to see, is what's so-called the box constraint, meaning that, for example, for the TV model, you don't take alpha from 0 to plus infinity, but you restrict it to some compact interval. Okay, you restrict it, and then if you are restricting, you are in a compact interval. This is lower semi-continuous, so existence of optimal parameter is guaranteed, and that's it. End of the story. Now, but this is a fictitious region, so to speak, because then you could also think, but then how small should this C0 be, right? Because then you have another optimization, because you don't know if you should be taking, well, slightly smaller C to have a wider range for alpha. So there is another underlying optimization problem here. So that's why I'm saying here that imposing these artificial restrictions can lead to suboptimal results. And then, of course, what we want is to work with maximal intervals. And then, okay, if we do so, what can we expect? Well, for sure, one thing that most probably is going to happen at the edges, you have some loss of structure. There is some at the borders, the regularizers may degenerate or look completely different. And actually, you can see here in the TV, if you take alpha equal to 0, this is 0. You are not regularizing at all. If you take this too big, you are over regularizing. So alpha at infinity. So at the border, something does happen at the edges. So then what we want is some analytical. Well, first we want to understand what happens at the edges in general, and how can we address it, and also optimal conditions to guarantee. So, sorry, let me rephrase this from the beginning. So if the optimal parameter is at the edges, probably this means that you are not, so for this kind of training data, this is not the best regularizers, because in the end, the optimal wants to go somewhere else. Okay, so first of all, this is telling us that for that specific class of data and similar images, this is not a good regularizers. But then the question is, do we have conditions that will tell us in advance, is this going to be a good class of regularizers? So means that you stay in the family, or I should look to another family, because for these images, these are not good, so let me look for others. Okay, So this is the questions that we wish to address and that I'm going to address. Again, we were not the first ones. There were people before considering problems where they take maximal domains. They don't impose these fictitious restrictions. I'm not going into details of these works, but I would like to mention anyhow, because we should give credit where credit is due. I do wish to highlight how we differentiate from these works. So what is the novelty in our work as compared to these ones here is that these works, the analysis is really tailored to the kind of parameters that you have. It's problem-tailored analysis. And what we developed was this more unified approach to which, for example, includes all these classes that I've shown in the previous slide. So this gives a unified approach, and in particular for a quite wide class of parameters, in the sense that our parameters can live in an arbitrary first countable topological space. Okay, and like I said, this provides a unified framework to deal with parameter learning that goes beyond structural stability, and we test the applicability of our approach in 4 families of regularizers of distinct nature. As you'll see 4 different families to which we apply our theory that look completely different from one another, and they can be all tackled by the same theoretical results. So now in the next few slides, I want to tell you, like if it was the trailer of a movie. I'm going to briefly say what our work is about, then I give more details, and then I show the applications. Okay, so the story starts like this. So we start with a single data point. The paper actually is written for an arbitrary finite number of data points, but here, for the simplicity of the presentation, I will restrict to 1, but we could address finitely many, okay, data points. So you can start with a family of pairs of noisy and clean images. This lambda, capital lambda, will always be first countable topological space, which is the domain of where our parameters live. Okay, and for the moment, I will call the parameters lambda. Then for each application, I will change the name, but the capital lambda will always be the set of where our parameters live. And we have a family of regularizers. Okay, that the domain is in L2, and the reconstruction functionals that we look at are these. So the fidelity term is always measured in terms of the L2 norm, and what is going to change is the regularizers. Okay, so this is the setting, and here I'm repeating, and then we look to our bi-level scheme, and this is what I've shown you before. So we have our reconstruction functionals for each lambda. We look for the minimizers. If it is unique, this is a point. It is just, but it can have more. So I look at the set of minimizers, which is this capital K lambda. I have my minimizers, and then I have my cost functional. So I will measure the distance again in terms of the L2 norm between my minimizers and the clean image. And I want to minimize with respect to lambda. This is going to give me the optimal parameter that I should choose for this class of noisy and clean images. And then the overall plan is going to be like this. We are going to introduce a suitable notion of stability for these lower level functionals, and which means that it's going to be closed under gamma convergence. I'll come to that. And because gamma convergence gives convergence of minimizers, automatically we will guarantee that this bi-level problem has a solution. There is an optimal lambda, period. Okay. Now, in many instances, for example, when the set of parameters is not closed, the family is not going to be, will not satisfy the stability condition. So then we have a problem. We have to understand what happens then. And then what we do is we are going to introduce a suitable extension of our cost function. And it comes like this. The idea, I will then go again through this in a bit more detail, but essentially we extend our reconstruction functionals through gamma convergence. We extend them, then we look to the minimizers as before, but now there is a bar, there is a closure because it is for this J bar. It is just as before. We collect all the minimizers, we have our cost functional, and then we want the optimal one. Okay, this is an extended bi-level scheme. And by construction, it turns out that this extended bi-level scheme does have a solution. But then you ask, okay, I have the original bi-level scheme, I have now this extended bi-level scheme, and we want to understand what is the relationship between both these two. And it turns out, under suitable assumptions that I'm going to present to you, this extended cost functional is nothing but the relaxation, the lower semi-continuous envelope of the original one. Good. And then because this is lower semi-continuous, and if the closure of lambda is compact, then you automatically have solutions. Okay, and if you prove, and then I mean this comes out of, say, typical calculus of relations arguments. Minimizing sequences for the original cost functional will converge to the minimizer of this relaxed one, and then I will apply all these things to explicit families or functionals. One that involves learning the optimal weight, as I was presenting before for the TV. One that we vary a certain amount of locality. We also going to learn a certain optimal integrability exponent and tuning the fractional parameter. These are the 4 applications that I hope to have time to go at least briefly and show what are the main properties that we derived. Okay, so now this was a trailer. Now let me give you a little bit more of the details, and let me start what are the standing assumptions. So these are our regularizers, and we assume that the domain is in L2 and it's non-empty. That's nothing special there. And we are assuming also that they are weakly L2 lower semi-continuous. Of course, if they are not, we can relax them. So we are assuming from the very beginning they are L2 weakly lower semi-continuous. These are our standing assumptions. We always be assuming these from the beginning to the end. Now there is a J that should not be here, and it has to do because we take, this comes from the paper, sorry. This is just a typo here for the presentation. It has to do when we take more than one training data. Okay, it comes from there. Let's forget about the J. And because of the assumption, simply the reconstruction functionals have a minimizer by the direct method of the calculus of variations. Compactness comes from the fidelity term. You have the L2 norms, so you have compactness from there. Lower semi-continuous, you have a sum of 2 lower semi-continuous functions, you are fine. So existence of solutions for a fixed lambda for the lower levels is guaranteed. So the set of minimizers is non-empty, period. Now we want to understand what happens at the level of the cost functional, the upper level. That's what we want to address. And for that, like I said in the preview, I'm going to introduce a notion of stability, which makes use of gamma convergence. And in case there are some people that are not so familiar, I will go over here quite quickly. If you are all familiar, that's great. You know this slide already. So if you have a family of functionals and a functional F, you say that your family gamma converges here with respect to the L2 topology. If you have this kind of lower semi-continuous properties, so whenever you take a sequence that weakly converges to a U, then this inequality holds true. Conversely, for any U, you can find a sequence that weakly converges to U, and the reverse with respect to lim sup holds. Of course, if you put the two together, greater or equal than lim if, greater or equal than fu, then in the end you have an equality, you have a limit, and that's why also sometimes this is referred to as the recovery sequence condition. So because it really provides a recovery sequence. And what I also would like to recall here, because we are going to use more than gamma convergence, also the Moscow convergence, and this means that the second condition is achieved with a sequence that converge not weakly but strongly. So the difference between gamma and Moscow is that the recovery sequence is with respect to the strong convergence in O2. And the reason why we like so much gamma convergence for this study of minimization problems is that it really behaves well with respect to minimizers, meaning if you have a family that is equicoercive, then you take a sequence of minimizers for your original sequence, and if U is a closer point, then it will be a minimizer of your limit functional, and you have convergence of energies. Have convergence of energies, you have convergence of minimizers, and all goes well in this minimization procedure. So then I am now ready to say what is this notion of stability. We say that a given family of functionals is weakly L2 stable if you take any sequence and you look to the corresponding functionals, if it does gamma converge, if it does gamma converge with respect to the weak L2 weak convergence, then the gamma limit has to be an element of your family. So what is in the family stays in the family. Okay, I don't know if it gamma converges, but if it does, it has to be to an element of the family. That's when we say that it is stable. And then an easy consequence of the fact that our functionals are equicoercive, that comes from the fidelity term and the direct method in calculus operations and the key properties of gamma convergence. You can prove that if you start from a weakly L2 stable family, then your bilevel scheme has a solution. There is an optimal parameter. End of the story. Okay, then you stop there. Now you may ask, well, if the family is not weakly stable, can things go wrong? Yes, they can. So this is also a necessary condition. Here, this is a very simple example. It's a toy model, but just to exemplify that from the mathematical point of view, if it's not weakly stable, then the cost functional I may not have a solution in the range. So here we are taking this open interval. We are assuming that clean and noisy image coincide, let's assume, and this is, say that we look at this reconstructed function. Of course, this is not interesting for the application point of view. You would never take this as a regularizer, but keep with me. So if you take this family, then you can prove when you take positive lambdas that converge to zero, so they are converging to a border. If they converge to zero, this is the gamma limit. You can prove that this is the gamma limit. You get this L2 norm, and that does not belong to your family because your family is not defined for lambda equal to zero. Your parameters are not there. And then you can see that the minimizer for this functional, it is just this value that is equal to this because we are assuming that the clean and noisy image, they coincide. Then you can just plug in the cost functional. This is a unique minimizer. You plug in, this is your cost functional. If you want to minimize with respect to lambda to find your optimal lambda, the minimizer is lambda equal to zero. Does not belong to your family. So you cannot guarantee that the minimizer, the optimal parameter, it is in the range that you started with. Okay, so this is to prove that the weak stable is also a necessary condition. Okay, but in many instances, we will not have a weakly L2 stable family. So then what we do, we go to this extension procedure. So let me go into the details. So we take the closure of our initial set, and then we assume, this is an assumption here that of course then in practice we have to verify. We assume that for each lambda in the closure of our set, these gamma limits, they do exist. This is like a relaxation. This is the lower semi-continuous envelope. You take, you fix a lambda in the closure, you take any sequence converging to lambda, and then you look at this gamma limit. You have to prove that they do exist. Okay, one thing. Then you look at the minimizers. You collect all the minimizers. As before, in the same notation, this k lambda, it is the minimizers of these extended functions. And then you look at the extension functional, which is as before. It is just a minimization from your reconstructed images, the distance between those and your clean image. So this is the cost function. This is how we are going to set up this extended problem. Now, note one thing. This is not, I mean, the notation may be a bit heavy, but there's nothing a big deal here, because these extended functionals, they coincide with the original ones inside in gamma. So we are only changing at the borders, because we are assuming that our original functionals are lower semi-continuous. This is our standing assumption. If they were not, we would relax them. So they are lower semi-continuous. So whenever lambda belongs to the original range, we are doing nothing. So we are just changing at the boundary. So this is, of course, an extension of this family. And because of this fact, also, this only changes at the border. So the cost functional, when you look at parameters that are in your original set, is the same. It's only being extended at the borders. I mean, that don't belong to the original set. That's all we are doing, okay? And then we look at this extended bi-level parameter with all these extensions that, as we have seen, we are not doing that much of a special thing. We are just extending in a natural way to the closure of lambda. And by construction, this family is weakly L2 This was constructed exactly as the gamma limit. So it's L2 weak stable. So this means that this problem has always a solution. Okay. But this is the extent problem. We want to retrieve information, if possible, from the original one. And this is how we can proceed. So this is going to be our main theorem. That's where also the Moscow gamma convergence comes into play. Remember, this is when the recovery sequence is with respect to the strong L2 convergence. So if this Moscow L2 convergence exists for the family of regularizers for each lambda in the closure, and whenever I take a lambda that belongs to the closure but not to the original set, I have to have a unique minimizer. So these are the two main assumptions that then in practice we have to verify if they hold or not. If these two conditions they exist, then this extension that we were defining before is nothing but the relaxed functional of the original I. There is this identity when we extend it trivially by infinity. So we have this identity. And too much. Sorry, so this is just some remarks on our main theorem. Of course, if the regularizers they Moscow converge because the fidelity term is continuous with respect to this Moscow convergence, then also the extended reconstruction functionals they do Moscow L2 converge and they decouple in the same way, fidelity plus reconstruction. And this estimate holds true without these assumptions on Moscow convergence and uniqueness of minimizers at the extreme values. And also one thing that we prove, because you could wonder if the assumptions in the main theorem are really necessary, as they are. If they happen to fail, then this identity may fail. And then we have examples, explicit examples where we prove these facts. And as a corollary to the main theorem, if the closure of lambda is compact, then under the same assumptions of the main theorem, Moscow convergence plus uniqueness of minimizers at the border, then there exist solutions to the extended cost functional, which coincides with the infimum of the original one. Any sequence of any minimizing sequence for the original cost functional will converge to a minimizer of the extended one. And of course, if it happens, if you happen to know that the minimizer, so the optimal parameter, lives in the original lambda, then it is a minimizer for the original one, and you retrieve an optimal parameter for the problem you started with. So this is the general framework. These are the main theorems. Then we want to see how these translate into practical relevant families of functionals. Let me start. Sorry. Let me start when we are learning an optimal weight factor. So here we are going to call it alpha, the same way in TV, because it works in a very similar way. The range of the weight factor is from 0 to infinity, excluding the extreme cases. And the regularizer is going to have, so this weight parameter is a multiplicative constant factor, okay? And then this is the reconstruction functionals as before. And what we wanted to understand is, does the bilevel scheme has a solution? If not, how does the extended one looks like? And I mean, see what then things look in practice. And if you remember, one of the main things to apply our main theorem was to prove the Moscow convergence of these regularizers. And of course, this does not go without assumptions. So let me first tell you what are the assumptions. We assume that R is convex. It vanishes exactly on the constant functions, and the domain is dense in L2. And we assume also that R is lower semi-continuous in L2. And under these assumptions, then the standing ones, remember the domain not empty, and they are weakly lower semi-continuous, this holds true, because convexity plus lower semi-continuous gives weakly lower semi-continuity. And also, there is always an existence of minimizers for the reconstruction functionals. Of course, you always want to make sure that you are not working with an empty set. So let me give you examples of functions that do satisfy those assumptions. For example, when you take the total variation in the local case, or if you want to look at a non-local functional, you could look at something like this. So here this G is 0 only at 0. So this means that it only vanishes at the constants. And then you have to take a convenient kernel so that the other assumptions hold. And for example, you could take this function that is related to the fractional Sobolev regularization. So these are examples that do satisfy the assumptions I was mentioning before. And under these assumptions, then we can prove that the family of our family does Moscow converge for any alpha in the closure. Now, from 0 to infinity, including 0 and infinity. And it goes like this. Well, as we already have observed, if you are in the original set, nothing changes. It is the regularizer you started with. At the borders, something happens. And at 0, you are not regularizing, you get 0. At infinity, you only get, this is the indicator function for constants. It's only finite for constant functions. And then, remember, so to apply the main theorem, we would have to prove Moscow convergence. Here it is for all parameters in the closure of lambda, and we would have also to prove that the values in the border that don't belong to the original set, we have uniqueness of minimizers, and this is, in fact we have, and these are the unique minimizers at these borderline cases. Then you can just plug in these things into our cost functional, and then this is how our cost functional looks like. Again, like I mentioned before, in the original set, nothing changes, it's the same. And then at the borderlines, then this is our cost functional. So this is how it looks like. And then because I and 2i, they hold, then we can apply the main theorem, means that this I bar is nothing but the lower semi-continuous envelope of the original cost functional. You have existence of solutions for this extended cost functional, but then of course then you want, but are there cases when we can expect that actually the optimal parameter is not attained at the borderlines but inside the original set? Yes, again, this does not go without assumptions, and here they are. So if you, on top of the first two, you assume further that the energy in terms of the regularization measured at the clean image is smaller, strictly smaller than the noise at the noisy. And this is a natural condition, because you want your regularizer to prefer clean image over the noisy ones. So you want the energy to be smaller at the clean images. So that is a natural condition. And because we are in a minimization procedure. And then if these other conditions, which means that the distance from your noisy image to the clean image is smaller than the average of the noisy image to the clean one. Again, there are some cases in which we can prove that this is reasonable, namely, if you have moderate noise, meaning this is the noise, so the distance between the noisy image and the clean image, if it is small, then a certain parameter delta. I'm not saying that it has to be small, it is just a delta number. And then if you have a somewhat non-trivial ground truth, so it is a bit away from being a constant, your clean image, measured in terms of this delta, then you can prove that this condition holds. So there are cases in which you can prove that these two conditions hold. And then if you assume all of them, so from the very beginning, then the original bi-level scheme does have a solution. So this means that for data that do satisfy these conditions that I was just presenting, these are good regularizers. The optimal parameter is found within the family that you started with, and such parameter does exist. Okay, and that also one thing that what did I do? One thing that we also show with examples is that if you drop any of these conditions, then the optimal parameter can actually be reached at the extremities. So this is something that we show the optimality of these conditions. And let me also mention that a related statement can be found in this paper by Delospace from Lieb and Valkonen. Now let me go, if I have the time, let me go to the next application, which is where we are going to study, say, the optimal integrability exponent. And the motivation that comes behind is that in this imaging business, you often find different LP norms. So that's why we were addressing also this, trying to find what is the optimal integrability exponent. So here, our parameter is called P, which is the integrability exponent. The range, the admissible range is from 1, including 1 to infinity, but excluding infinity. And our regularizers then look like this, some kind of LP norm for these non-local functions. So these double functionals. And again, if we want to go over our procedure, a key step is as before, we have to address the Moscow L2 convergence. And this is, I guess, what I'm showing here. No, before that, of course, I mean, to have the Moscow convergence as before, we have to have some sort of assumptions. And here in this case, we are assuming that f is a character function, so measurable in the first two variables, continuous in the second two. We have a certain growth from above and below. I'm not going into the details. And we are assuming also that f is separately convex in the two last variables. So you fix one, it is convex within the other one, and vice versa. Okay, and if you assume these assumptions, then the standing ones, remember the domain is non-empty and the regularizer is lower semi-continuous, this holds true. So that with that we are fine. Again, you want to make sure that you are not working with the empty set, so of functions, so simple ones that do satisfy the assumptions I was showing in the previous slide look like this. So for example, here, A, it is just an even function that is bounded away from 0 from below. This is another function that does satisfy for certain parameters the previous assumption. So we are not working with the empty set, good. And then what can we say under the assumptions I was showing before? What can we say with respect to Moscow convergence? Well, as before, if your parameter is in the original set, nothing changes. The regularizer is the one you started with. Something happens at the borderline. Here it is for P at infinity, where you get this essential supremum. So it's no longer an integral functional. It is of a different nature. You get this essential supremum function at the P equal to infinity. Now, if you remember, for us to apply the main theorem, we need Moscow convergence. It is here, but we also need that at the points that are in the boundary and don't belong to the original set, we have to have uniqueness of minimizers. So this is the next thing that we have to verify. And for these to hold true, we need a further assumption, namely, one too many, yeah, here it is. We have to assume that F is jointly level convex in the last two variables. That means that the sublevel sets are convex with respect to the two last variables. And in this case, the supremal functional also becomes level convex, and then you can prove that the reconstructed functional at p equal to infinity has a unique minimizer. And then if you put for the other cases, you have existence of minimizers, not necessarily unique, but with that you don't care. We only care about uniqueness of minimizers at the extreme points that don't belong to the original set. And then if you put all these assumptions together, you can plug in and find what is the extended cost function. It looks like this, nothing changes for original set, and then here it is, you just put here the unique minimizer for p equal to infinity, and then as before, this extended functional, it is the lower semi-continuous envelope of the original one. You have existence of minimizers, you can put the machinery working, and everything goes well. Now, of course, here again, you want to understand, well, are there cases where the optimal parameter is actually this p at infinity, so that this essential supremum performs better than the integral ones? Yes. We also give an example of cases in which this may happen, but we also study somewhat general case of functions f, integrants f, that is more restrictive than what I was presenting here. So there are more assumptions on top of that, in which then you can prove that the optimal parameter stays in the family that you started with. Okay, so now time to move to the third application, where you want to optimize a certain level of non-locality, which is measured in terms of a parameter that here we are calling delta. Again, the range for this non-locality parameter is again from 0 to infinity. And actually here in this case, we addressed two classes of functionals. One that was not introduced by Aziz and Nguyen, but they fully studied this kind of functionals. I will present them to you, but these were original proposed by Morel and co-authors in the early of 2000, and we are also going to address a class of functionals that was introduced by Oberhan Kornprost, both in the context of imaging processing. And as you're going to see, it turns out that the both families that are non-local functionals, as the parameter converges to 0 to this borderline, you get a local version. So you get a TV, a multiplicative of the TV. You recover the TV model in the limit. So let me start with the Brazil-Nguyen framework. This is the class of regularizers. Here you have the delta both inside and outside. It measures the non-locality in your problem. Now I'm going to present here the list of assumptions that they deal with. It's huge. It's not that difficult. I'm not going to the details. It is just for the sake of completeness. There's nothing too special about it. They are lower semi-continuous in the interval 0 to infinity, continuous except at a finite number of points. You have a certain bound from above. It is non-decreasing. You have a normalization condition, and it's positive if t is positive. Okay, it's a long list, but nothing special about these conditions. We are just importing the ones that they were considering, and of course, again, you want to make sure that there are functions that do satisfy these conditions. Here are two examples of such, and it comes out as a corollary to their study. In this case, the regularizers are never convex functionals, never convex, but still the standing assumptions they do hold, and you can prove that there exist minimizers for the associated reconstruction functional. And then what we have to address and this goes a bit beyond of their work because they studied like gamma convergence with respect to in L1, but we need something stronger. We need Moscow L2 convergence. We need a recovery sequence that converges L2, converges strongly in L2. That's where we had to work a little bit harder. But of course, our starting points are used that live in L2, not in L1. Okay, but using many results that they proved, we can prove that our family does Moscow converge in L2. Again, in the original set, nothing changes. At 0, and this is something that they proved already, they have a gamma convergence result in L1. What you get as delta goes to 0, you recover a multiplicative of the TV. So you get the local, you start from a non-local functional, you get in the limit a local functional, and at infinity, you are doing nothing, you are not regularizing, okay? And I guess here I'm showing, because the results are very similar in nature for the class of functionals introduced by Oberg and Probst. Here the assumptions are simpler. So rho is a non-negative function, non-increasing, and this is the you can think of it. Does not have to be a smooth modifier, but it could be if you want. And then this is the class of functionals that they were addressing. And again, under these assumptions, our standing assumptions, they do hold, so there is no problem there, and there is solutions for the lower level functions, for the reconstruction functions for each fixed parameter. Then what we have to show is this Moscow convergence, L2 convergence, and it's in the same spirit as the case of the Brazilian case. Nothing changes when in the original range. You get now a different constant, but you get a local functional and delta goes to 0. You get the local TV case, and 0 for delta equals to infinity. And here again, you have uniqueness of minimizers for delta equal to 0 and delta equal to infinity. So you can explicitly write your extended cost functional, and you can put your machine to work, and go. Everything goes as before. And here we can prove again by working on some examples. We provide simple examples in which these extreme regimes actually can occur. So the optimal parameter can go either to delta equal to 0 or delta equal to infinity, in which case you are leaving the family of regularizers that you started with. Okay, and then as the final application, which I just have just a couple of slides, I think, about that, and then I'm done. But this is again is a case of a completely different nature from the previous one, where we are trying to learn the optimal fractional parameter, and the motivation comes from this paper where they show that by using a fractional Laplacian as the regularizer, it can lead not necessarily to better results, but more efficient numerical algorithms. There was already a previous paper in the literature dealing with trying to learn the optimal fractional parameter. The difference between our approach and this one is that they impose some kind of fictional penalization in order to stay in the class of regularizers that they started with. Like I said, we don't want to impose such conditions. We want to work with the maximal range parameters, which we do. And just to give you a brief flavor of this case, so here the order, the parameter of interest is this S, and S over 2 is the order of the spectral Laplacian. S lives in the open interval between 0 and 1, and this is the regularizer that involves the delta norm of the fractional, the Dirichlet fractional Laplacian. And then what we prove here. Again, we have to establish the Moscow convergence, which we do. Nothing changes if we are in the original case. Then look at what happens at the borderlines. For S equal to 0, you recover the L2 norm of U, which is not, I mean, in terms of imaging, is not a good regularizer, you are doing nothing. And for S equal to 1, you get the norm, L2 norm of the gradient, which is too much regularization, too much regular for image. For image, you want to allow for discontinuities. So here, in this case, you really want to get away from the border cases, otherwise this is not a good family to start with. And in this case, actually, and that's why I also wanted to mention very briefly, I'm not introducing the notation behind here, but here we again, as in the first case, we give full conditions by exploring some differentiability of the extended cosine functional. We can prove, we exhibit conditions on the data that guarantee that your optimal parameter will be within the true fractional regime, which is what you want, because as we've seen, the border ones are not interesting in this case. And well, I guess I leave the details for our preprint, and with that, I thank you for your attention.